Hey everyone, welcome back to Yulan's channel. Today we'll be continuing our AP psychology journey, and today we'll be talking about auditory sensation and perception. We discussed the visual perception and sensation in our previous videos, and also like a general understanding of perception and sensation. So if you haven't watched my those videos, like sensation and perception, please do so because some of the things are overlapping, and it's really good to have like a background knowledge before we start. So yeah, let's begin. Your sense of hearing is often called audition, but how do we hear sound? It happens when the vibration of sound waves are converted to neural impulses. Each vibration causes molecules to compress and expand. The greater the compression, the higher the amplitude, and the louder the sound. Another characteristic of a sound wave is frequency, the number of complete wavelengths that pass a certain point in 1 second. This also works for the wavelengths, like for division, in color. The frequency determines the pitch, which is how high or low a sound is. The shorter the frequency, the higher the pitch. However, even if the same note pitch is played on violin and flute at the same volume, you will notice that they sound different. This is because of the difference in timbre. Sound is measured by the amplitude of the sound waves, with decibel unit, dB. Parts of the ear. Your outer ear, which is often called the pinna, is where the process begins. The pinna channels the sound wave into the ear canal. Then a mechanical chain reaction sends the sound waves down through the outer ear to the eardrum. The eardrum is a tight membrane, and when sound waves hit it, it vibrates. Right after hitting the eardrum, these three bones in the middle ear, hammer, anvil, and stirrup, pick up the vibration and transmit them to the cochlea. So cochlea is over here, the snail-like thingy. The cochlea is where the physical stimuli of a sound wave is converted into a neural impulse, which is transduction, as you all know. Vibration from the middle ear causes the oval window, which is cochlea's membrane, to vibrate, pushing the fluid inside the cochlea. In the cochlea is the basilar membrane lined with hair cells that are bent by vibrations. These hair cells transduce mechanical energy into neural impulses, similar to the processes that happen at the retina in the eye. So we talked about the visual anatomy in our last video, so please check it out. The hair movement triggers impulses in nearby nerve cells that form the auditory nerve. Similar to the optic nerve, which is for the eye, the auditory nerve sends messages to the thalamus, which are sent to auditory cortex in the temporal lobe. So, occipital lobe is mainly for vision, whereas the auditory cortex is the temporal lobe. Note that the inner ear contains the semicircular canals in the vestibular sacs along with the cochlea. This works when we'll talk about this in the vestibular sense, which is together with kinesthetic sense are the body position sense, which is really key in how we actually control our body in the space. Now you may wonder, just like you could lose your sense of sight, those such as nearsighted, farsighted, and you could lose your hearing sense. These are the two major types of hearing impairment. The first one is sensory neural hearing loss or nerve deafness. So it's like the damage to the auditory nerve. As a result, the signal is transferred to the cochlea but not to the brain. This hearing loss is often caused by heredity, aging, and being exposed to too much noise, such as rock or rap, or just a lot of headphones, etc. If someone had nerve deafness, they could have a cochlear implant inserted. This device converts sound into neural impulses, just like the cochlea would if it functioned properly. This is the only way of restoring the sense of hearing, but it is not very effective in adults. Conduction hearing loss is a second type, and is the damage to the system that conducts sound waves to the cochlea. This may be damaged down to the eardrum or the middle ear bones, which are the three ear bones, anvil, hammer, and stirrup. A hearing aid is used for this less common form of hearing loss. Now we have two series of pitch perception. So how do we actually hear different pitches? The first one is place theory. Oh my god, I forgot to place a E here. The place theory explains how we hear high-pitched sounds. Developed by the Gord von Baxi, it links pitch with the location of the basilar membrane, and it is stimulated because certain hair cells are attuned to certain pitches. Because high-pitched sounds have a high frequency, it will peak near the close end of the basilar membrane. However, low-pitched sounds have a low frequency. Its peak will be near the far end. Then the brain automatically assumes that the sounds near the close end are high-pitched, while sounds near the far end are lower-pitched. Our second theory is the frequency theory, also called temporal theory. It explains how we hear low-pitched sound. It suggests that the rate of neural impulses traveling up the auditory nerve matches the frequency of a tone, thus enabling us to sense its pitch. But this is from the definition of frequency theory, because an individual neuron can only fire at a maximum of 1,000 times per second, but neural cells with alternate firing can achieve a combination of 4,000 firings per second. This is like 4 times. This, called the volley principle, explains why we can hear low-pitched sounds. These two theories explain why we hear low and high-pitched tones, but what about those mid-tones? The volley principle explains that since neurons cannot fire more than 1,000 times in a minute, some neurons alternate firing. These neurons then fire in succession so fast that they create a combined frequency above 1,000 waves per second. A quick note that we measure sound in decibels. 0 decibels equals absolute threshold for hearing. A rock band at close range is about 140. A normal conversation is about 60 decibels. Now we have our final section of this video, localization of sound. Having 2 ears, just like having 2 eyes, is much better than having one. The placement of our 2 ears on different sides of your head allows us to determine where sounds are coming from. If you are sitting in class and your buddy to your left calls your name, the sound waves of his voice will hit your left ear before the right because it has a bit more distance to travel. This is how we localize sound. But when the sound is coming from behind you, above you, in front of you, or below you, it is much more difficult to locate a sound. Therefore, tilt your head to help you locating a sound. Do so gives your ears different intensities of a sound, making it easier to locate the source. So if you are interested in the content, please like and subscribe to my channel. Thank you for listening, and we'll talk about we're finishing up unit 3 in our last 2 videos about chemical senses and body senses. So chemical senses involves your gustation and olfactory, whereas body senses are the vestibular and kinesthetic sense. So yeah, keep an eye on those videos that will be coming up in the next 2 days. Thank you.